Alright, welcome back. So here's my second example on linear systems with differential equations, and here I'm going to use again a matrix method. The system we're going to take a look at is x dot equals negative 1/2 x plus y. Y dot is equal to negative x minus 1/2 y. Matrix version of this sucker. So imagine we have a vector x which has a x and a y component. We'll make it a capital, kind of bold it a little bit, dot it. And it is equal to coefficient matrix, negative 1/2, 1, negative 1, negative 1/2, times my vector x. Bold that sucker a little bit. So what I mean again by the vector x is a component x of t and y of t, these functions that I'm trying to find. So then capital X vector dot would be again the derivatives of these suckers right here. Now looking at the coefficient matrix, we can pull a couple of things out of it. Before I do that, I'm going to write the characteristic determinant, negative 1/2 minus alpha, or excuse me, gamma 1, negative 1, and then negative 1/2 minus gamma. Two ways to do this. One, do the regular determinant idea, which is to multiply the main diagonal and then subtract the other diagonal from it. If you do that, you're going to end up with a lambda squared. Can't seem to call that thing the right name, huh? Alpha, gamma, lambda. And then here, when you clean it up, a trace is the sum of the main diagonal. Negative 1/2 plus negative 1/2 is going to be a negative 1. We want the opposite of that for the coefficient here. So that's going to be plus 1 lambda. And then the constant term, after you again do the determinant of this sucker, could also be found by looking at the determinant of the coefficient matrix, which is the product of the main diagonal minus the product of the off diagonal. So negative 1/2 times negative 1/2 is positive 1/4, and then I'll have minus negative 1 times 1. So 1/4 plus 1 is 5/4. If we set our determinant equal to 0 and solve, and then what we should find here is that we have complex solutions for lambda. So lambda is going to be negative 1/2 plus or minus I. So you can go through that to confirm that that's true, but I'm pretty sure it's right. Now think back to our systems, or not our systems, but our second degree differential equations, constant coefficients. We get our characteristic equation, which looked a lot like something like this. And every linear system of differential equations in two variables can be turned into a second degree equation in one variable, and you'll get a similar characteristic equation here. What we found when we were doing the second degree equations is that if we had complex characteristic roots, that really we only needed to consider one of them. We didn't really need the conjugate. That was sufficient because the sine and the cosine gave us independent solutions, two independent solutions. So again, my point here is that really I only need to consider lambda 1, which is negative 1/2 plus I. Now, to get the solution to this, I am going to need to find an eigenvector to go along with this eigenvalue. To do that, I need to plug in my negative 1/2 plus I here, and then multiply this particular matrix by a vector, let's call it V1 is equal to A1, A2. And when I take that A1, A2 times this, plugging in my lambda 1, what I should get is negative 1/2 minus negative 1/2, so that goes away, minus I. So I'm going to get a minus I A1 plus 1 A2. And I set that equal to 0, just like up here. Cleaning that up a little, I get that A2 is equal to I times A1. Now if I let A1 equal 1, that implies my eigenvector could be the vector 1, I. So if A1 is 1, 1 times I is I, and so that's A2. That is going to help me come up with my solution. So from here, I believe that vector x is equal to the eigenvector 1i, and again we'll get into how this is going to work when we turn it into a real solution, times e, and again when I take this to me by power of e, the sum allows me to break that into a product. I'm going to have negative 1/2 t for this part, plus in the power turns into a product, and we know from Euler's equation that e to the I is a sine plus I cosine. So then I'm going to get, cosine plus I sine. So then I'll get the cosine of, that's a 1i, so I'll have cosine of 1t plus I times the sine of t. Now if I break that into component parts, that means I'm going to have 1 times all of this stuff, I'm going to have I times all of this stuff, along with the e to the negative 1/2 t. So I'm going to rewrite this in a slightly different way. I could also think of this as e to the negative 1/2 t times 1 times the cosine. Now, the 1 times the sine, that's going to be imaginary, so I'm going to separate this out into real and imaginary parts. So I'm going to pull out the I times e to the negative 1/2 t. And so I'm going to have a sine of t up here from the 1. Down here, when I multiply through by I, I'm going to have I cosine, which is going to put the cosine over here in the imaginary portion. And then I'm going to have I times I sine. I times I is negative 1, which is a real component, so that goes over here, negative sine of t. That's a parenthesis there. So again, I have this vector cosine negative sine t, this other vector sine of t, cosine of t. And so the top line are my x solutions, the bottom line are my y solutions. As far as the I goes, it's just a constant, so that from our previous work we know we can just separate it out. So what I'm going to have here is e to the negative 1/2 t for the x part times the cosine of t, oops, sorry, I forgot my little c1 here, constant, plus c2 times the sine of t. And I don't have to worry about the I in my real solution here. As far as y of t, that's going to be my bottom line, which is going to be e to the negative 1/2 t, which both parts have in common. And then, now as far as the negative, it's going to kind of get sucked into the constant, but I'm going to put it in there. I'm going to have a negative c1 sine of t plus c2 cosine of t.
I can hear you.
Hi, Michelle.
That's not right.
My wife's complaining because I'm out late at night on my patio under the full moon doing differential equations. So these are my two solutions. So what I want to look at next is what's the phase plane of these solutions going to look like? The vector field, how do they flow through there for different constants C1 and C2 depending on the initial conditions. So let's take a look at that next. As far as the phase plane goes, which is again a nice way to look at solutions, it doesn't work the same way as real stuff. The relationship between the eigenvalues and eigenvectors isn't as straightforward as it is with real solutions. So I can't just look at them and get it. I got to play around a little bit. Oops, I'm supposed to underline that. Phase plane, or this is also called a vector field. And we'll draw it in two ways, with solutions in there and without. So as far as the vector field phase plane is concerned, that's related to the slope at a particular time. Oops, it's supposed to be an x, dy dx. Well, that's going to come from y dot over x dot. Our y dot was negative x minus 1/2 y, and our x dot was negative 1/2 x plus 1y. So if we can generate slopes that way. So for example, let's suppose I was focusing on the point 1, 1. I want to know what the direction of the vector is through the point 1, 1. My equation here tells me that the slope through that point, the vector slope at that point, is going to be negative 1 minus 1/2 over negative 1/2 plus 1, which is going to give me what? Negative 3/2 over 1/2, which is going to be a slope of negative 3. So I should expect the vector passing through 1, 1 should be negative 3. So that gives me a direction and a magnitude on that vector there. Other ones will have a different, thing going on. Suppose I picked like, let's say 1. Let's do 1/2, 1. And the slope, the vector through that point would be what? Negative 1/2 minus 1/2 over negative 1/2 times 1/2, negative 1/4 plus 1, which gives me negative 1 over 3/4, which would be negative, what, 4/3, so negative 1 1/3. So same height of points here, but just moving a little bit in toward the origin on the x part, I should see that it's a lot less steep. Looking at the solutions, and again, we could calculate all day points, but it's kind of nice with technology today. We can use a program to generate that pretty quick. Solution down here tells me a couple of things. Cosine plus sine parametrically is going to give me something circular or ellipse-like, and the e to the negative 1/2 t is going to, as t increases, to drive it to be smaller and smaller. So what we're going to do is we're going to take ellipse kind of paths, but as we're making that ellipse, we're going to shrink our radius. So what I should find is that I'm going to have spiral in toward the origin. The direction of the spiral is something I have to figure out by looking at a couple of slopes at different points near each other, and I'll be able to identify that slope. Let's grab a program to help us do this. So here, this is a program I've listed on our differential equations website. And so I just come up here, and for dy dx I type my y dot over x dot. And half the time, because usually when we write the systems, we write x dot and then y dot underneath. Be really careful about the order. What's the numerator? What's the denominator? On this particular program, multiplication has to be identified by a times, otherwise you'll get an error in the error box down here. So here's my y dot over my x dot. I chose a -3 to 3, -3 to 3 for x and y to match another program we're going to look at. But here you can see that kind of spiraling going on in here. And we can try to do an Euler method solution on this too. Let's see if I click here. Yeah, it kind of loses it. You can see it spiraling in here, but then the Euler's method loses track of it and it starts to get a little wacky. So it should continue to spiral in, following through, and it's going to keep pulling itself in to spiral toward the origin. MIT has a really, really nice in their phase plane program, in their differential equations course, first order systems, phase portraits. It's their applet. Right here, there's directions on using it there. But it's pretty straightforward. I identify what my trace is here, which is I calculated -1. Back to the notes to confirm that. It's always the opposite of the trace here. The opposite of -1 is a +1. And then identified the determinant. We found it was 5/4, which is 1.25. And then we tweak the value of s, which is going to be this number right here. And so you have to move s around till you identify that number, and this one will always join it. So getting the trace and determinant correct gives us this pair of numbers. Moving around s here will give us this off diagonal. And so here you can see that's my coefficient matrix, and that shows some of the curves spiraling in. And again, look at the similarities to these solution curves. So there's, what do I have? 1, 2, 3, 4 solution curves here. And again, that's a phase portrait. It's a parametrization based on these equations down here. So if we had initial conditions and we solve for C1 and C2, x of t and y of t together would give me one of the solution curves, of which I'm seeing 4 different ones here. So a particular C1, C2 is going to give me like this curve right here, or that one right there. Cool thing here on the MIT program is I can pick a particular initial value like right there, and it will draw the solution curve for me. And when I click there, it tells me what point I'm at down here. So again, pointing over here, I can try and get on the x-axis. And then maybe I want to try and get to 0.30, so I can get kind of close to it. I have my fancy pen here. It's probably a little easier with a mouse. And then I click, and it draws that solution curve in for me. So I can put a whole bunch in. Lots of fun. Again, compare that to the slope field where we can see that coming in. And again, the Euler's method kind of loses track of things pretty quick. You can play with the step size on the Euler method. You can give it initial condition manually instead of pointing to it here. So you get a couple options for that. But for a lot of these, the Euler's method just doesn't work too well. But we can see the general trend of this spiraling solution and the solution curves here. Again, just the slope field alone, just drawing those segments doesn't tell us the direction, but when we take something like the 0.11, it has a slope of -3, I can use that to determine direction in the slope field. So the 0.11 is somewhere over here, around here somewhere, and the -3 means from that point I'm going to be going this way, and then this vector is going to pull me that way, and this vector is going to pull me that way, and this vector is going to push me that way, this vector pushes me that way, and I'm going to keep getting pushed in and around and in and around from that slope field. So the system can be used to generate a slope field. It's pretty awesome. So that's it for the complex one. So again, just a quick review. You can use the characteristic matrix, take the trace, opposite of the trace. Again, trace is the sum of the main diagonal, is your coefficient here. The determinant of the coefficient matrix gives you your constant term. Set it equal to 0, solve that quadratic equation. If your roots are complex, you only need to consider one of them. I could have done the minus, it doesn't really matter. I chose the plus. And given our work with second order differential equations, I know that the complex roots in Euler's equation are going to give me two independent solutions related to sine and cosine. I get to strip the I out, and I can break it down for x, two independent solutions, y, two linearly independent solutions. And so this is my solution there for the whole system. Initial conditions, x of t equals 0, whatever, y of t equals 0, whatever, allow me to solve for c1 and c2. Not too bad. You guys are good at that kind of algebra. So, complex numbers aren't as bad as they seem. Vector fields by hand are a pain in the ass, but these programs are just beautiful, ain't they? Check that out. Alright, enjoy, do good math. I'll catch you later.